Okay, so welcome everybody to today's IAMP One World Mathematical Physics seminar. It's my great pleasure to introduce Gaultier Lambert from the University of Zurich, and Gaultier will tell us about the universality for free fermions point process. So Gaultier, we're looking forward to your talk.
Okay, so thank you very much for the invitation and the opportunity to speak. I'm very happy to speak at the mathematical physics seminar. So the topic of the talk is to talk about statistical mechanics model, which come from free fermions and describes the correlation function of this point process in the large n limit. So it's some joint work with Alex Deleporte, who is in University d'Orsay in Paris-Saclay, and this is based on this preprint. So the plan of the talk is first to give an introduction to the probabilistic model that I will consider, and it will be on RD for arbitrary dimension. Then I want to explain as a motivation the relation in dimension 1 to random matrix theory, and motivate a bit the question I want to consider. And what I want to present, the result I want to present is what are the limiting correlation function for these point processes. Okay, so if you have any question, just let me know at any time. Okay, so just the model. So I mean, it's very basic. So the quantum state of a single particle, which is confined by a potential. So I assume that the potential is a function v from Rd to R plus, is given by solving the sort of Schrödinger equation. So minus Laplacian plus v. And since I assume that v, so if v is growing, this operator has a discrete spectrum. So there is a set of eigenvalues that are non-negative and increasing. And in particular, I put this small parameter h bar square in front of the Laplacian. So this is like a Planck constant, if you want, and all the quantity that is the eigenvalue and eigenfunction will depend on h bar. Okay. And I assume that the eigenfunction are normalized in L2, and in particular, because this operator is self-adjoint, they form an orthonormal basis. Okay, so what I mean by free fermion is I consider the ground state of capital N fermion, and there is no interaction. So the ground state is just given by a Slater determinant. Okay, so this is the usual Slater determinant. So the wave function is a simple determinant, and the normalization here is such that psi n is normalized. So in L2 of R, so d times n, and then it's under and it's normalized to have norm 1. Okay, so. Okay, so this is the convention. Now, so the setting is the following. So I will choose n in such a way that I filled up all the energy up to a certain level mu. So what this means is I fix a parameter mu, which is, if you want, the Fermi energy. And I choose a particle number n to be just the number of eigenvalue below mu. Okay, so this is such that I consider all state below a certain energy, and I will be interested in the limit where h bar tends to 0. Okay, so just now about the model. So you know the interpretation is that I have this wave function here, which depends on n particle, which depends on n coordinates, and I can view that as defining a probability measure on the space of configuration in Rd to the n. So here it's a random configuration, and the probability, its probability I associate to be just basically this psi n square. Okay, And because it's a square of a determinant, I can write that as a determinant of a certain kernel, which comes by making the product of those matrices. And in this context, the kernel I get is this sum over the eigenfunction. And, you know, I chose n in such a way, maybe I should rotate actually. Yes. So I choose n in such a way that this kernel here is the kernel of the spectral projection. So the operator, which is the indicator, that minus h bar square Laplacian plus v is less than or equal to mu. Okay. So this comes from choosing n so that I sum up over all energy level less than mu. And this is a nice convention because this makes the link with spectral theory. And basically you can study this kernel as a kernel of this projection, okay? So what I'm interested in is the correlation function of this point process when n tends to infinity. So let me show you that because of this special structure of determinants here, you have a nice expression for the correlation function. So to compute them, I just take a function f, which is symmetric, and it takes a k coordinate, and I try to compute this expected value. So then, okay, but this is the definition. And in particular, if I expand the determinants here in the probability, I get a sum over a double sum, in fact, over all permutation of Sn of this product here. Now, the point is that in this formula, because it's only dependent on the k first coordinate, you can integrate basically xk plus 1 up to xn. So I'm sure you have already seen this type of computation. And this forces the permutation sigma and tau to agree on those indices. So when you do this, you get that, okay, you reduce the integral from Rn to Rk, and then you get sum over all possible injection from k to n, and you have a permutation tau, but now of the symmetric group Sk, which remains here. And basically this, if you recombine this sum with the sign of the permutation with this guy, this is just an expression for the depth of the kernel pi n applied to xi xj. Okay, so the bottom line of this computation here is just that this here is called the case correlation function. So this is a or k-point function sometime. And for free fermions, this can be expressed entirely for any k only in terms of this kernel pi n. Okay, so this structure is called the determinantal point process in probability theory. So it's a general definition here. So if the correlation function of this measure Pn are all of the form depth of a certain kernel, so what it means is that Pn is the determinantal point process with this kernel pi n. In more mathematical physics terms, this is just a Wick theorem for free fermions, the fact that you can express everything in terms of this pi k, and maybe you have heard sometimes pi k is called this is called a reduced density matrix. Well, at the probabilistic level, you know, it's kind of nice to have a determinantal structure, because this helps you to, for example, write down a generating function for the point process. So if you take the expected value of such a product, where again, this is the xj here as a random configuration, then this is a Fredholm determinant. So this object is a Fredholm determinant. And here pi n, again, is this operator, which is coming from the indicator that minus h bar Laplacian plus v is less than mu in our case. And g minus 1 is just a multiplicative operator in this case. Okay, so the point is that you have very nice formula. And in particular, the question I want to answer is what are the asymptotics of this correlation function rho k as h bar tends to 0. As we will see, there are, well, you need to rescale properly to define the asymptotics, and that's what I want to explain. This will, because of this special determinantal structure that they are all written in terms of a kernel, this will in the end boil down to the asymptotic of this kernel. Okay. So before presenting our result, I want to make a detour by random matrices, just to explain, to give some motivation in dimension 1 to study determinantal point process in this model. Okay, so I will consider the simplest example of a random matrix ensemble, which is the following measure. So you take a measure on the space of n by n Hermitian matrices with weight exponential minus 2n times the trace of m square. Okay, so what this factor here, this weight is, you can just rewrite it as exponential minus 2n, the sum over all I and j of mij square. Okay, so what this is saying is that actually under this measure, the entries, this factorizes, so the entry of the matrix are IID. So IID, well, actually not IID, there is the Hermitian constraint. So there are independent, sorry. So this is independent entries, which are Gaussian. So complex of diagonal and real value on the diagonal. So this model is called, the GUE, or Gaussian unitary ensemble. And it's really the simplest example of a matrix model. So, and because of this trace here, you can actually compute explicitly the joint law of the eigenvalue of this model. And this is the formula that you get. So if you integrate the eigenvector, which are uniformly distributed, you get the following joint density for the eigenvalue of M, which is just this product here square and then times the Gaussian weight. And this was, I mean, this can be interpreted as a Coulomb gas. This is what Dyson did, but you can also, in this special case, because of the power 2 here, is due to the fact that the matrix is Hermitian, and it leads to the following nice algebraic fact. So you can rewrite the product I and j of xi minus xj. This quantity, in fact, you can write as a determinant of pj xi. Okay, so this is the n by n determinant, and you can do that for any monic polynomial pj of degree j minus 1. So that means that you can choose your favorite family of polynomial of degree j minus 1 monic, and then this determinant is always equal to this. So you can replace in this formula the square here. And what this will give you is that Pn, you can rewrite it in the following form. So there is a normalization constant times the determinant of some phi j square. And the function phi j are just my monic polynomial pj times the Gaussian weight. It's just come from putting the weight inside. And what choice do I want to make? You can choose a polynomial in such a way that they are orthonormal with respect to this weight here. So this is what I wrote here. The integral is just delta ij times a normalization constant. Those factors here, they will determine the n. But the point is that you see this has really, again, a free fermion structure. I mean, it's like a Slater determinant square, except that instead of having the eigenvalues, the eigenfunction of the Schrödinger operator as the phi j, I now have some polynomial normalized by their weight. So those are sometimes called orthogonal polynomial ensembles. And okay, so in the case of the GUE, for this example, you can, so the orthogonal polynomial with respect to the Gaussian weight are Hermite functions. Okay, so they are classical, they are the Hermite function. and they satisfy a differential equation that can write in the following form. So -1/4 n square times Laplacian plus x squared phi j is this quantity. And what this means is that this you can go back to the original model. These are the energy. They depend on n, and this is and here you get h bar from there is 1/2n. Okay. So in other words, those phi j are they are the eigenfunction of the Schrödinger equation with this potential. And what this means is that the GUE is really just it's a probability measure which you can view either as the eigenvalue of these Gaussian matrices, or it also comes from looking at the ground state of free fermions confined by the potential v of x is x squared with h bar is 1/2n and mu is 1. Okay. So right. So this is an observation, and so you can, I mean, this, for example, you can use this to plot the eigenvalue of this point process on the computer by just sampling the matrix. And here is a histogram that you see for the eigenvalue. So this is n is equal to 100. This is the eigenvalue, and you clearly see that they distribute according to this red curve here. So this curve is called the Wigner semicircular law, because it was found out by Wigner, who basically introduced this method in the 50s. And you can see it's plotting it here. So the point is, so what did Wigner show? He showed that if you look at what's called the empirical spectral measure, okay, so this is a probability measure where you put a delta mass at every one of the eigenvalue. So this random measure converges almost surely to this red curve here, which is this semicircular density. Okay, so that's what he showed, and I'll give a proof of this later. Now you can do a more general model where you replace the Gaussian weight here by a general potential. So this is what you get. So you take, for example, v, an analytic function which grows faster than the logarithm, and then you can look at the eigenvalue of a n by n Hermitian matrix with this measure. So exponential minus n trace of v to the m normalized. So this condition here, it's used to so that Zn makes sense, and the claim is that the eigenvalue of this matrix model, they are also determinantal, and the kernel is a projection onto the space of polynomial of degree strictly less than n in L2 of R with the weight. Okay, so this is the general feature, and here is what happened in general. So you have a potential V, that's V in blue, for example. And the claim is that, I'm not going to prove this, but the empirical spectral measure for this more general model, it converges to a density rho, which depends on the potential V. So this is, for example, this density in red here. And the density has compact support. In fact, the support has a finite number of disjoint interval, and generically you get square root vanishing at the edge point, just like the semicircular law. Okay, so this is the density of state for this model, and you can ask the question, what are the asymptotic of the correlation function for the random matrix model, both in the bulk and near the edge? So in the bulk, that means that I will look at the limit of the correlation function around the point x naught in the middle of the spectrum. So, and in this case, so if you take a point x0 in a cut, then and you zoom in around x0, so this is here the local density. I mean, this is the number of eigenvalue around x0. So that's the correct scaling. To get density, I mean, well, to rescale the process. And then the claim is that this converging distribution to a universal point process, which is called the sign point process. So this is in an example of somehow Wigner vision that the eigenvalues of random matrices and other objects should be universal in the limit as n tends to infinity. And you have a similar statement at the edge. So if you take, for example, if you zoom in around one of the edge points here at the edge of the spectrum, then the scaling is different. It's n to the 2/3 times a certain constant, and it also converges to a universal process, which is this array process now. And for this particular model of unitary invariant ensemble, this was proved. So this is, I think, in 1999 by in generality by Dave, Krischer-Bauer, McLaughlin, Benekedes, and Tao, using Riemann-Hilbert techniques. So there are much more results, but okay. So again, to come back, so if you look at the G, so this is a sample of the GUE spectrum. So what it's saying is that if you look at, for example, at the edge and you multiply the picture by n to the 2/3, you see a universal point process, which is this array process. And similarly in the bulk, if you take a zoom in, for example, in around this point here, and you multiply by n, then you see a sign point process. And this is a convergence in distribution. So what are this point process? So the sign process is a determinantal point process on R with this kernel. So it's just a sign. One way to think about it is that, so the kernel is translation invariant. I mean, it only depends on the difference between X and Y. And you can rewrite it as a Fourier transform of the indicator of a ball of volume 1. Okay.
Sorry, can I ask you a question?
Yes.
So there's a question from the audience, and the question is whether is there still a free fermion picture for the Hermitian matrix model with general B?
So no, I don't think there is a correspondence. I mean, because so the GUE is really, so you see, basically, so in the Hermitian matrix model in general for general V, so let me change this, so maybe in red so that we see. So you get, in general, you get the orthogonal polynomial time the weight, and those are orthogonal with respect to this weight. So the only case where these sort of function which satisfy a Schrödinger equation are basically the classical polynomials, such as Hermite or Jacobi. So those are the case where there is a random matrix model in the background. In general, okay, it's in general there is no mapping between the two processes, but nevertheless, when I will present my result on free fermions, you get the same limit. That's the thing. So it doesn't matter whether, well, they are in the same universality class, basically. I hope this answers the question. Yes, so the point is, okay, so what is the array point process? So rather than writing the formula for the kernel, I want to give the following description. So the array point process is the determinantal point process on R with a kernel which is the kernel of the projection of this spectral projection here. So and okay, so why is it called the array kernel? Because if you actually look at this operator, so if you try to solve this equation, sorry, I should not write it like this. So if you try to solve the equation minus Laplacian plus x phi lambda is equal to lambda times phi lambda, the solutions are explicit. So in a generalized sense, phi lambda of x is just the array function evaluated at x plus lambda. Okay, so those are the only solution of this equation, which decays at plus infinity. And okay, so you can express this kernel in terms of the array function. So that's why it's called the array kernel. But I like to think of it as the kernel of this projection here. We will see why later on. So this is the definition of this universal limit here. And not only it's known that they hold for those matrix model, but they hold for other random matrix model, which I mentioned, such as Wigner matrices. Okay, I don't want to enter so much into the details. So let me present our result about the free Fermi gas. So let me go back to the model. So now the probability measure that I consider, that I introduced on the endpoint, is just 1 over n factorial times this det of pi n of xi xj, and pi n here is the kernel of the spectral projection. So, and mu is fixed, this is important. And then the potential V, I will assume that it goes from Rd to R plus. This is just a convention, I mean. And it's smooth, and the important thing, it's smooth on this set, okay? So this set is compact, that's important. And outside of this set, basically, it's not important what V is. As long as it's L1 lock or some mild condition, it's fine. No smoothness is required. Everything will happen here for any small delta positive. So this is the assumption on V, and the limit I take is h bar goes to 0. So it's really a semi-classical limit. And what happened in this semi-classical regime? So there is a famous Weyl theorem, which is very old, which is concerned the number of particles. So this n here, number of particles, is just a trace of this kernel or operator here. And okay, it has the following asymptotic. So this is basically telling you that this is up to a constant. This is of order h bar to the minus d. So as h goes to 0, the number of particles diverge in this way. Z mu is positive. And this omega is such that if you integrate, so this is an integral over Rd over a ball of radius omega d, okay? The Lebesgue measures, then you get 1. So it's like the radius of the ball in the dimension which has Euclidean volume 1. So this is a universal constant in other words. Okay, so this is Weyl's law, and in fact there is a more precise version which concerns what happened for the diagonal of this kernel. So it's basically telling you that if you normalize by 1 over n this kernel, then it converges to a probability density function. So this is a probability density function. So it's normalized. This z mu here is the normalization constant. And this measure is basically mu minus d of x, the positive part, to the power d over 2. Okay, so this is valid for any v. And this is what I will call the density of state. Why? Because, okay, you can rephrase, so our first result is that you can rephrase Weyl law in terms of those Fermi gas, so give a probabilistic interpretation. So this is the following. So for any small epsilon, if you look at the distance between this empirical measure, so remember that those points are random under Pn, they are distributed like the position of the free Fermi gas. This is empirical measure, its distance to the density of states is basically converging to 0 exponentially fast. So for any epsilon, you get a rate of exponential minus n epsilon square. So in particular, the particles, they are very close to rho. And the distance here can be a Wasserstein distance, Wasserstein 1 distance, for example. Okay, so let me give you an example. So we go back to the GUE, so x squared on R and mu is 1. Then you see you recover the semicircular law there. If d is 1, you get just this measure. So this is one way to prove Wigner theorem for the GUE. This is here a plot of the density for the following model. So mu is 1, and you take the potential, a quartic potential, so x1 to the 4, x2 to the 4 on R2. And then you get this type of bump. Okay, I mean it's what it is. The point is if V grows, if this set is compact, then this is always have compact support. I mean, okay. So now let me present my main result about correlation functions. Okay, so we have the following. Yes. Okay. Sorry. So we have the following theorem. So it's again there is two cases where you are in the bulk and at the edge. So maybe I illustrate here. So So first, if you are, so this is in the bulk, okay? So this means that I zoom in inside the support here. So this is where I take my point x0 inside of the support of the density. Then you see this is the same scaling as I had for the random matrix case, except that I have a 1/d here to account for the possible different dimension. And then this point process, so zooming around x0, it converts to a determinantal point process on RD, which is translation invariant, and its kernel is again given by through its Fourier transform, and its Fourier transform is just this indicator function of a unit ball here. So this is exactly the analog of the sine process in a higher dimension. So we have K1 is basically the sine process. So it's sine pi x minus y over pi x minus y, just like in random matrices. So and I have a similar statement at the edge. So if I take a point here x0 at the boundary, so the set where v is equal to mu, and I will assume that the gradient of v is different from 0 at this point, which is the case here. So that means that it's somehow a generic edge point. Then I'm claiming that you see we saw this 2/3 before. So if I just sorry, there is a minus sign missing, of course. So it's fixed. So if I zoom in at scale h to the 2/3, so in a small neighborhood here of size h bar to the 2/3, then I see a universal scaling limit, which is a determinantal point process again on RD with a sort of generalized area kernel, which is the projection of minus Laplacian plus, so this quantity arise, so the gradient of v at x0 dot x, okay? So this is an operator on RD here, and negative. So again, when d is equal to 1, you recover the area kernel, and in general, it's an easy generalization. So this theorem, it provides somehow some generalization of the law of random matrices in higher dimension, you know. So point processes are natural. So there were, I mean, this especially the limit at the edge. I mean, and in the in physics, I mean, this observation, this result, they are due to Dean, sorry, Le Dussal. Majumdar and Gregory Scher. I think it's this. And they have a couple, they have a series, several papers on the subject. So you can find a reference in our preprint with Alex. So they computed this kernel and this one first by physics argument, and they also studied many other things about these point processes. Okay, so let me present the idea of our proof. So I want to explain at a very high level why those kernel arise. Sorry, I think no zoom. Yeah. Okay, so so in general, so one thing about the proof of this theorem is that because all the processes involved are determinantal, in general, it suffices to show that the correlation kernel converges to the limiting one. I mean, it's just an algebraic fact. Now, if you look at the point process where you do an affine transformation, so you recenter around x0 and you multiply by a certain scale epsilon, which we think of being small, then you see this point process, its kernel Kn is associated with the rescaled operator, where I again do an affine transformation. So the Laplacian is scaled like this, and the potential is also as an affine transformation. So in particular, what's happening here is that this I can linearize, so it's v of x0 at the first order, right? And And in particular, this tells me what the scale in the bulk is. So if I choose epsilon to be of order 1 over h bar to cancel this factor, then I basically, and the constant I choose in such a way, then I basically get this indicator function here. It's very formal. Okay, it just comes from this square root of mu minus v of x0 cancel this and this. So basically, what is happening is that if there is to be a limit, then the kernel of this operator should converge to the kernel of this one. And the kernel of this operator we can compute because we can diagonalize the Laplacian using the Fourier transform. And the kernel of this operator is just this guy. And basically, this is what I called, KD of xy. So the claim that it is to show is that this Kn here, which is the kernel of this process, so it's epsilon to the d times pi n of x0 plus pi n of x0 plus epsilon y, it converges to this. So this is what we have to prove. So I'll give you a sketch of the argument later on. Let us look at what happened at the edge. So if you're at the edge, well, you start from the same thing, but now the Taylor expansion is slightly different. So this is v of x0 again, but v of x0 is equal to mu at the edge. Remember, at the edge point, v of x0 is equal to mu. So I get mu plus epsilon, sorry, it's a gradient of v of x0 dot x at the leading order. And now this mu cancel. And I really see that if I want to cancel this factor with this guy, the correct choice is epsilon is h to the 2/3, which is a correct scale at the edge. And if I do this, then I expect that the limit is really this operator that we have seen. So this is what I had called KRED. Okay. So how do you prove that the kernel really converges to the correct limit? So let me explain the argument in the bulk. I'll point out a few differences at the edge. So the idea is really to use spectral theory, and it relies on the fact that this. So let me call this operator H, capital H. So this is the Schrödinger operator, and in fact it's a pseudo differential operator, a Weyl pseudo differential operator with semiclassical parameter H bar associated with this symbol. So xi square, this comes from the Laplacian, plus v of x. Okay. And in particular, our proof relies on the calculus for a pseudo differential operator. So let me remind you what this notation here stands for. So if I have a symbol A, then the op of A is just, so it's an operator whose kernel as a function of xy is distribution valued. And it has the following form. So there is a Fourier factor here. With h bar in the face, and then here the symbol appears. So this is basically for every k. What this is saying that for every k I have such a Taylor expansion. So the kernel has this integral where I have a function ak here plus a remainder which I can make arbitrarily small by choosing k large. And this function ak here, it has a sort of Taylor expansion. So it has an expansion with a0 up to h bar to the power k times ak. And all those a0, ak's are smooth function with certain condition, okay? So it depends on the class of symbol you consider. But anyway, this is the formula. And it's nice because there is a functional calculus. So what this means is that if you take a smooth function phi, so with compact support, this operator is positive, so I can assume that it's defined only on R+. So the point is that so if I take phi of this Schrödinger operator, so this is my H, then it's again a pseudo differential operator with a new symbol A, and I know some things about A. So the leading part, the principal part, A0, is just given by phi of the symbol of this operator, so xi square plus v of x. And moreover, all the coefficients here, the ak, they are supported on a small neighborhood of the support of phi evaluated at this point. Okay, so this is pretty nice, and this you can use to study these point processes. So let me illustrate how you get the Wiles law very quickly. So remember, so H is this, and we are interested in the operator pi n, which is just the indicator function that H is less than mu for a fixed mu. So this is this curve in orange here, and you can approximate it by smooth function phi plus from above and phi minus from below. Okay, those are smooth compactly supported function on R plus. And okay, so the point is that this is a quantity you want to compute, because Wiles law is telling you what is the diagonal of this kernel. So for any test function f, so this is a trace of f pi n, and because everything is H is self-adjoint, you can bound it by trace of f phi plus of H and trace of f phi minus. So bound from below and above. And if you look at this plus minus, at these traces here normalized by 1 over n, you can use the pseudo-calculus, pseudo-differential operator formalism to write it in the following way. So you get this factor, and then you get to the leading order, so the error is of order h, you get a0, the principal part at x and c, f of x. And this a0 here, it depends on whether you consider plus or minus, but it basically just, it's this quantity, okay? And remember that this quantity, they squeeze the indicator function, okay? So, up to losing some epsilon, I can replace this basically by the indicator function of something less than mu. Okay, and if now I can integrate over xc, this gives me a rescale volume of a ball over just mu minus v of x0, and then I get this factor. So this is basically what the proof boils down to, because from this formula I can identify, since everything is a probability measure, that this guy will converge to a constant 1 over z mu as h bar tends to 0. And this trace here, which is squeezed between this and that, which is the expected value of the sum over the number of particles, it converges to the integral of f of x times the density of state that you read off here. Okay, so this is how you do Wiles law. So now what about correlation functions? So for that, you need something a bit more complicated. You need to get an approximation of what's called the propagator. So the propagator is this quantity. So it's this, it's really the quantum propagator. So it's exponential of AIT times H, your Hamiltonian, over H bar. And I will do that for T in a small neighborhood of 0. And for convenience reasons, you multiply by a cutoff. So this chi is just a cutoff. It's any smooth function with compact support, okay? So this whole operator, the claim is that it has an integral kernel, which is again distribution valued. It looks almost like a pseudo-differential operator, except that the phase is now phi t of xc instead of just the Fourier phase. And then I have a symbol AKT. Now it depends on the time. So this is the difference. So you have phi t here and a t there. The error here I didn't mention previously. This is controlled from L2 to L2 in general. So it's an operator which you control from in the norm L2 to L2. And in general, you can upgrade this control to a trace class. So G1 for Schrödinger because of the nice ellipticity property of the Laplacian. Okay, I don't want to enter into those technical details, but we had good control of the error. So, and what is phi? So phi is the solution of the following Hamilton-Jacobi equation, which is associated with the classical dynamics for H. So it starts from this condition. So at time 0, it's just x galaxy. And this is normal because you see, if you take, if I take t is equal to 0, so this is 1 at t equals to 0, okay? And basically I should recover the previous theorem here, which was with this guy. So this is from the previous theorem, right? And I mean, at time t equals to 0, I know the expression of phase 0 from the previous theorem. It's this quantity. So it's my cutoff chi applied to this variable. And the phi, it satisfies the following Hamilton-Jacobi equation. So the derivative in time of phi t is given by this quantity. So this equation is well posed, at least for small time. So it has a unique solution, which is smooth, you can show. And in general, the way the theorem works is that you fix a compact set, and for x and y in this compact, there exists a small tau such that this formula holds uniformly in T in this small set. And the error here is controlled, for example, L2 to L2 or in the trace norm. Okay. So the point is that how do we use this? So there's one step I'll mention very briefly is that so remember that so actually it's written here. So the operator we interested in is the spectral. So it's the spectral projection of h less than mu. So and we will approximate it by a smooth spectral function. So you have this indicator function, and you take phi h to just be this indicator function convolved with a modifier p of h bar, and you take a modifier at scale h bar. So what this means is that this is really just the microscopic scale, and you can assume that this p actually there's a typo here, is support of it's support of the Fourier transform, of course. I mean, so I am assuming that the Fourier transform is a small compact support. Okay, and then the claim is the following. So you can use some Tauberian theorem argument to show that actually, so this pi n, its kernel at the local scale minus the kernel of phi h at the local scale are close. So the important statement here is you gain this factor. And this is true for in a compact set as long as x0 is, say, in the bulk. So this means that this claim, I'm not really explaining it, but it means that you can study this function phi h of the Hamiltonian phi h of h instead of pi n. So this is a reduction step. It's quite classical, in fact. And the point is that now phi h we know very well. Why? Because you can write rho h in terms of its Fourier transform. So you write it as its Fourier transform time, well, this factor here. And then you see when you put h here, this will give you a propagator here. So you can use this expression here of the propagator to write the following formula. So phi h, you know its kernel as a function of xy is just this factor times the indicator of r d plus 2. There's this indicator function, and then here there is a complete phase which is involving this phi t and a symbol akt. And the point is that basically, like a00, that's what we know, a00 of xc is equal to chi of x squared plus v of x. Okay, that's okay. So, and in particular, you choose your cutoff always. So let me draw in green chi. The chi is always 1 on a much larger interval. I mean, it's a smooth function, and it's basically equal to 1 on a very large interval. I mean, so it will play no role. This is just equal to 1 in the regime I will consider. Anyway, the point is that, okay, so this expression we like because, okay, first of all, the error can be made arbitrarily small here. And okay, but it's not the point. The point is that it's really like here in the phase, I have a 1 over h bar. So as h bar tends to 0, this will become widely oscillatory, and I will be able to apply the stationary phase method. Okay. So the point is you apply the stationary phase method. This is really the idea. And let me sketch the argument. So first of all, I've chosen rho to have a very small support so that I can explain the phi t for small t. And if you look at this Hamilton-Jacobi equation here, you can calculate the expansion of phi for small t. So it's the initial condition x dot xi plus t times vx plus xi square plus the big O of t square. Okay, and if I plug this expansion into the phase, what we see is that the x0 here and there will cancel. The h bar will cancel in for this factor. So this gives me what I want. And then the rest is plus t times this certain quantity here. And when I apply the stationary phase method, the idea is that basically, because this is 1 over h bar, I look over the critical points of this function. And you apply the stationary phase method in the variable which are t and lambda, which are conjugate variable. So if you differentiate this, maybe it was bad, I need to put it in orange. So if you differentiate this with respect to t, you find this equation should hold. And at with respect to lambda, you just find that t is equal to 0. Okay, so so this is the equation for the stationary point. So basically, it determines the critical value lambda is just xi square plus v of x0. Okay, and so if I apply the stationary phase method, so I have 2 variables. So this killed one of the h bar. So I get this factor as my approximation at the leading order. I set t is equal to 0, so I get a00 here, which I've told you is basically equal to 1. And then I get this. This is what is left of the phase. And then in this quantity, I put lambda being the critical value, so xi square. So basically, that's where my condition that I should have mu strictly greater than v of x0 for this argument to work. Otherwise, you see that there cannot be a critical point because xi is positive, so this would make no sense. And this is basically the answer. I mean, this kernel is exactly what I wrote as kd of xy. So in contrast, if you are at the edge, and I'll conclude with this, if you are at the edge, then t is equal to 0. And basically, xi becomes equal to 0 in this integral. So you get a double critical point, and that's where the airy behavior comes in. I won't do the computation, but it's classical that in this case, where the Hessian degenerates, you get airy type behavior. So let me just conclude. Just to remind you, so what I consider is the ground state of a free Fermi gas, which is the following probabilistic model. So it's a probability measure Pn on configuration on n points. Those points live in Rd, and it's given by this letter determinant of a certain kernel, where the kernel is related to a Schrödinger operator for an energy level mu fixed. And the number of particles is just trace of this kernel. And I'm interested in the limit as h bar tends to 0. And I give you basically 2 main results that if you are in the bulk, so x0 is in this set, then this is the microscopic scale in the bulk. And if you rescale the kernel at this scale, then it converges to this kd, as I explained, which is the Fourier transform of a ball. And what this means probabilistically is that if I rescale my point process around x0 at scale epsilon, then it converges to this universal determinantal point process with kernel kd. So that's in the bulk. And then at the edge, I need to further assume that the gradient of v is non-degenerate, so as a vector. So this is like for a generic edge point. And then the scale is slightly different. There is this factor 2/3 that I try to explain here. And then the kernel rescale, it converges again to a universal object, which is this airy type kernel in d dimension, which you can represent as, I don't know why there is an R floating around, as a kernel of the operator, which is minus Laplacian plus gamma dot product with x is negative. You can express this explicitly. I'm just not writing it. And the point is that the rescale point process at the edge, it converges again to a universal point process, which has this generalized airy kernel. So thank you for your attention.
Okay, thank you very much, Gaultier, for this very nice talk. Any question or comments from the audience? So I think I have one. So concerning the edge result, of course, it's crucial for you that, I mean, it's crucial that the gradient of V is non-zero at the point x0, right? So this, it's very important.
Yes.
So do you have any, I don't know, is there any, I mean, what do you expect instead if you are at the critical point? I mean, if the gradient is zero?
Sure, I mean, so you can get many different behavior, in fact. So let me go back. Where was it? Yeah, so it was here. So you see, I mean, like, so basically, if the gradient is zero, then you need to go to a higher order, right? Mm-hmm. So if the gradient is zero, then this would be mu, and then I would get epsilon square. The second deviation of V, right? And then let's say at xx, right? Something like that. Mm-hmm. So if the Hessian is non-derivative, is non-degenerate, right? I mean, first you will get like, so it will be 1/2, I think. So this is due to the fact that if the gradient is zero, let's see, in the picture, you know, the density would be very smooth here. So there would be much less particle, right? Mm-hmm. It would vanish at a higher order. So you see a smaller scale here, h bar to the 1/2, basically, or larger scale, depending how you see it. And then the limit should be, so it should be just this operator, basically. I mean, you should have something like x the Hessian of this, sorry. I mean, you should have here a quadratic form, right? Like this, if this makes any sense. I mean, for example, if V is strictly convex, right? Or I mean, not strictly, but it's convex, so that this is positive, and this is a nice operator. I mean, okay, this is yeah, okay. Mm-hmm.
Okay, thanks. Other questions from the audience? I think actually I have. Yes, was there anyone saying something?
I have a question.
Yes, Jan.
First you used the pseudo-differential calculus.
Yes.
But then you introduced the Fourier integral calculus.
Yes.
Is it enough? I mean, is it sufficient to use the pseudo-differential calculus to get the result? Is it necessary to introduce the Fourier integrals?
Okay, this is a very good question. So I think that, okay, so basically, I mean, at the precision of Weil law, which is at a different, I mean, here we're really looking for microscopic information. So it's much more powerful to use the Fourier integral calculus because it gives you, if you want the convergence of the kernel, yes, you need to use it, I think.
Yeah, so you mean you get better error estimates if you use Fourier?
Yes, so basically, yes, so indeed, let's see, where did I write the result? Here. So, so what I'm saying is that you might be able to prove this result, just the probability side, without, with just pseudo differential operator. Mm-hmm. Now, if you really want the kernel converge here, the kernel convergent, which is the stronger result, in fact, then you need you need integral operators, I think, because you really need to, you know what I mean, right? I mean, if you would like to know that this converges to this as an operator in certain weaker norm, I can do it with by approximating with pseudo differential operator. If I really want the kernel to converge pointwise in the neighborhood of the diagonals, then I think I need a Fourier integral operator. I don't know how to do it otherwise.
Yeah, well, one of goals of semi-classical analysis, at least in the past, used to be to get error estimates which are as good as possible in terms of H bar. I mean, to get the best power of H bar. So does your method
Yes.
give the best power?
Yes, so it gives us the error is big O of h bar, which is the best you can do in general. That's correct.
Okay.
In the bulk. At the edge, it's slightly different. We actually, you know, things are different at the edge, because at the edge, so you can get, so you see there's two objects, right? So at the edge, we can get the good approximation for this guy with the best error, but the Tauberian theorem doesn't allow you to transfer it. I mean, basically, so I don't know if our error at the edge is optimal. That's what I'm saying.
Thank you.
Because of this step.
So actually, I wanted to ask you another question. So is it somehow within reach to try to derive this kind of precise asymptotics for minimizers of Hartree-Fock functionals? You know, I mean, now you're talking.
Yes, yes. So
yeah,
yes,
I mean, please, yeah.
I think we can do that. So this is something we want to look at definitely. I mean, so for the Hartree-Fock functional, we can do that, and then, you know, there's a. I think it's possible to also. Okay, this is maybe harder, but to then relate the Hartree-Fock model to the real interacting Fermi gas in some sort of mean field interaction regime.
Exactly.
That's something which I mean, yeah, which I think is so. It might be difficult on RD, but actually, if you do it on a torus like you did, then that's probably something to think about and maybe doable. I mean,
I would say I would just like to, you know, to take the Hartree-Fock functional with, you know, confining potential. I mean,
yes.
the set you consider, but then you have a, let's say, a mean field interaction among the particles, and then you could look at the minimizer of the Hartree-Fock problem and address the same kind of questions you address now.
Yeah.
And
so that you can do. That you can do. I think the semiclassical analysis, I mean, are possible for that. So my guess is that, you know, if you switch on an interaction, you know, and you look at the Hartree-Fock model, then you would get different limits, so which depend on maybe on the interaction kernel.
You think? Okay, I would have imagined that you get, let's say, in the bulk, the same type of result up to. I mean, you just have to rescale with a different row, which is going to be an. But I don't know. I mean, that's just.
Yeah,
nice.
it's a good point. I don't know. I am not so sure. I mean. It's a good point. So at some point, if your interaction potential is singular, clearly this has
sure,
to.
Sure.
Yeah.
Okay. Okay, thanks. Other questions or comments from the audience? Okay, doesn't seem to be the case. So thank you very much, Gaultier, again for the nice presentation.